In 1965, a young Caltech graduate student by the name of Gary Flandro was poring over his notes in Building 180 of the Jet Propulsion Laboratory, studying the intricacies of using planets' gravitational fields to slingshot spacecraft into the outer reaches of space with no need for additional propellant. The gravity assist, a method of propulsion that uses the gravity of a gravitational body to literally pull the spacecraft into a new trajectory and velocity. As he examined the possible trajectories, Gary noticed something incredible. In the late 70s, a window would open up where the alignment of the planets would allow for a single satellite to pinball its way between Jupiter, Saturn, Uranus, and Neptune, before eventually being spit out to the outer reaches of our solar system and beyond. With this knowledge, a flurry of activity began within NASA and JPL. A once-in-a-lifetime opportunity had been found that would not come about again for another 175 years. And it was imperative that the opportunity was not squandered. Planning began, and in 1977, two satellites, Voyager 1 and 2, would launch aboard the three-staged Titan IIIe rocket. Voyager 2 would utilize a gravity assist with Jupiter, Saturn, and Uranus before racing by Neptune, before it eventually exited the solar system, while Voyager 1 completed a more direct path, whipping by Jupiter and Saturn before venturing into deep space, moving away from Earth faster than any other spacecraft. Voyager 1 is now over 22.8 billion kilometers away from Earth. That's so far away that Voyager 1 is now outside the influence of the Sun's constant stream of solar wind, meaning it is now in interstellar space, officially reaching the region in August 2012. We, as a species, have now left our mark in interstellar space after a 35-year-long journey, a ponderously long time in the scale of human life, and that was with the help of multiple gravity assists. While we can build and deploy these technical marvels to investigate other worlds, sending ourselves into space is another thing entirely, and using gravity assists to visit our closest neighbours makes little sense. To date, the furthest humans have ventured into space is to the dark side of the moon, a mere 400,000 kilometers away. If our ambitions to create colonies on Mars are to be realized, humans are going to need a spacecraft that are faster and more efficient than the ones we currently have at our disposal. Mars is on average about 64 million kilometers away. The fastest and most efficient method we have to reach Mars using the Hohmann transfer method, with launch windows every 26 months, takes about 9 months to complete. Faster transfer times are possible, but engineers are stuck in a catch-22. It takes fuel not only to accelerate the spacecraft, but to decelerate it too. There are no disc brakes in space. The more we accelerate, the more we have to decelerate too. In order to carry all that additional propellant, engineers will be forced to sacrifice payload weight, reducing the space available for food, water, and other vital supplies for a crewed mission to Mars. We can take some solace in the fact faster transfer times will reduce the supplies needed and will reduce the crew's exposure to the high radiation of space. But what if we could achieve faster transfer times without sacrificing payload? What if we could achieve faster transfer times with even more payload? Let's first examine current technology to see where things could be improved. The Atlas V rocket that brought Perseverance to Mars utilized chemical combustion to propel itself, a method where a fuel and an oxidizer are combined in a combustion chamber and ignited. The resulting exothermic reaction causes the combustion products to rapidly heat up and expand. The nozzle design then directs the expanding gas in one direction to achieve thrust. Getting the most out of our fuel and oxidizer is the first step to maximizing our thrust per unit weight of fuel. There is a useful quantity engineers use to describe this property of fuels and oxidizers, specific impulse. We described in detail what this value represents in our last video on the X-15, explaining how it represents the total energy we can extract from our propellants per unit weight. In that video, we used this equation where specific impulse is defined by thrust force divided by fuel flow rate. This is an extremely important metric for our Mars transfer vehicle. The higher we can push our specific impulse, the less fuel we need to bring, which frees up space for payload. Or we can bring the same amount of fuel and increase our velocity to reach Mars sooner, or even be able to leave outside that ideal Hohmann transfer window. So, how do we improve specific impulse? The technology with the best specific impulse currently is ion propulsion. Take the NSTAR ion drive aboard the now retired Dawn spacecraft. This engine used electric power to propel ions and achieve astronomical specific impulses. The engine releases xenon atoms into an ionization chamber and then bombards them with high-energy electrons. The collisions produce a positive xenon atom and more electrons. These electrons are then collected by a positively charged chamber wall, while the positive xenon atoms migrate towards the chamber exit, which contains two grids, a positive grid called the screen grid and a negative grid called the accelerator grid. The high electrical potential between these grids causes the positive ions to accelerate and shoot out of the engine at speeds of up to 40 kilometers per second, which is vastly higher than what chemical combustion can provide, which has a typical exhaust velocity of about 3 to 4 kilometers per second. This exhaust velocity is paramount to achieving higher specific impulses. If we play around with the specific impulse equation, we can see why. Specific impulse equals the thrust force divided by fuel flow rate. Thrust force is equal to the mass flow rate times the velocity, while the fuel flow rate is the weight of the fuel on Earth, and thus this value changes to mass flow rate times acceleration due to gravity. And, as we see, the mass flow rates cancel themselves out, leaving us with only exhaust velocity divided by gravity. So, it's rather obvious. To maximize specific impulse, we need to maximize exhaust velocity, and ion propulsion is the best technology we have to do that right now. With 10 times the exhaust velocity, the ion drive can achieve 10 times the specific impulse. That's a phenomenal increase. So why aren't we using this technology for interplanetary missions? Mass flow rate may not be important to specific impulse, but it is massively important to thrust. As we saw just now, thrust force is equal to mass flow rate times the velocity. Chemical combustion happens extremely quickly. It is, after all, a controlled explosion, and so it is capable of accelerating millions upon millions of molecules out in a very short space of time, leading to a high mass flow rate. High thrust is very important for particular maneuvers, like capture burns, where a rocket will fire to slow its speed down enough to be captured by a planet's gravity. The window for this deceleration may only be a few hours, where ion propulsion simply cannot provide enough thrust in a short enough time to successfully complete the maneuver. Ion propulsion simply does not have the mass flow rate necessary to achieve high thrust. It took the Dawn spacecraft 4 days to change its velocity by just 94 kilometers per hour. To increase our ability to change velocity quickly, we need to increase the mass flow rate. To do this, we need to increase our input power. For ion propulsion, that power comes in the form of electricity, which provides the energy to ionize our propellant and accelerate it using an electric or magnetic field. Current generation ion-propelled spacecraft use solar panels to provide that electricity. The Dawn spacecraft has panels capable of producing 10 kilowatts of power when orbiting Earth, which diminished to 1.3 kilowatts by the time it reached its destination in the asteroid belt 3 times further away from the Sun. Scaling that solar power becomes impractical very quickly. NASA estimates that a Mars transport vehicle would need at least 400 to 2,000 kilowatts of power to carry astronauts and cargo to and from Mars. So, how do we power something like that? Nuclear power is the only thing that can give the power density needed to make this viable. This isn't a new concept. In 1961, the Atomic Energy Commission and NASA launched the Nuclear Engine for Rocket Vehicle Applications program, or NERVA for short. This program developed and ground tested 20 reactors before it was disbanded in 1973 due to budget constraints, but was recently revitalized when the US Congress approved $125 million in research funding for nuclear propulsion. There are two primary types of nuclear space propulsion: nuclear electric, which would power an ion drive like we saw above, and nuclear thermal, which was the focus of the NERVA program. So let's start there. Nuclear thermal propulsion works by harnessing the heat created during nuclear fission to provide the energy needed to expand and accelerate a propellant through an exhaust nozzle. Here, the nuclear reactors work in much the same way as a nuclear reactor here on Earth would, where a chain reaction of neutrons colliding with uranium atoms splits them and creates more neutrons and a tremendous amount of heat. To capture this heat, a propellant, typically liquid hydrogen, is pumped through the reactor core, which will cool the reactor core and pass the heat to the liquid hydrogen, which rapidly expands and accelerates out of the thruster nozzle at high speeds, typically around 8 kilometers per second, twice as fast as chemical combustion, and thus about twice the specific impulse, at around 887 seconds. However, it's not all sunshine and rainbows. Using hydrogen as a propellant comes with some issues. It can attack the fuel rods if they are not adequately protected with a material that is resistant to hydrogen's destructive tendencies. Liquid hydrogen also has to be stored at extremely low cryogenic temperatures, and if it is allowed to rise in temperature, it needs to be vented to prevent an explosion. And on top of this, the tiny molecule is so small it can slip through seemingly solid materials, as it can fit between the spaces of larger molecules. This makes it unsuitable for long storage periods, and ideally, we want a Mars transfer vehicle that can sit in orbit around the Earth or Mars for extended periods, waiting for the crew to arrive and begin its journey between the planets. Then, when it arrives, the crew descends in a separate vehicle, leaving the transfer vehicle parked in orbit once again. Liquid hydrogen is just a pain to use in this application, so why use it? Because when it comes to maximizing exhaust velocities and thus specific impulse, low molecular weight exhaust products are important. Assume for a moment that all the heat energy we input into the system is converted to kinetic energy in the exhaust products. Kinetic energy equals a half times the mass times the velocity squared. To find the velocity, we can rearrange this equation. So now we see that velocity equals the square root of 2 times the energy divided by the mass. It's clear here that increasing the mass of the exhaust particles will decrease the velocity of our exhaust. Hydrogen is the lightest element and thus maximizes specific impulse. If we were to use another propellant, it would be extremely difficult to make a nuclear thermal propelled spacecraft with a high enough specific impulse to justify its use. The next lightest gas is helium, which is twice as heavy as hydrogen, and thus will reduce our specific impulse by the square root of 2, nearly negating all the advantage nuclear thermal propulsion can provide. The next lightest element, which isn't a solid at temperatures we require, is nitrogen, which is 14 times heavier, and thus would decrease our specific impulse by the square root of 14, which is 3.7 times worse, making a nitrogen nuclear thermal engine worse than a traditional combustion engine. So, we can't get away from this hydrogen storage problem, and if we hope to use nuclear thermal propulsion, we are going to need to figure out how to keep hydrogen cryogenically stored for extended periods. If this problem could be solved, the higher specific impulse and higher thrust could cut our transfer times to Mars by half, or potentially open launch windows outside of the ideal Hohmann transfer window. So, can we get around this hydrogen storage problem while using nuclear power to achieve higher specific impulses? This is where ion propulsion becomes really attractive again. One massive advantage in ion propulsion's favor is its ability to use heavier, inert, and easily storable noble gases as propellants, like xenon or krypton. This goes against our previous understanding where low exhaust molecular masses are beneficial to higher exhaust velocities. This is possible because we are using electric power to launch these atoms at tremendous speeds. The ion exhaust velocity is defined by the charge of the ion, the voltage that it is being accelerated by, and the mass of the ion. The charge and mass of the ion are defined by the propellant choice, but we can scale that voltage very high before we hit a limit in performance due to material properties or some other physical limit. For combustion or nuclear thermal engines, we are converting thermal power to kinetic energy. That thermal power is difficult to scale. Chemical combustion is limited by the energy we can liberate from the chemical bonds of the propellants and by the temperature our engine can operate at before it melts. This is a problem for nuclear thermal power too, which has to run extremely high reactor core temperatures of 2,500 degrees Celsius to achieve exhaust velocities high enough to justify its use. Specialized nuclear fuel designs are needed to survive these temperatures, and any higher would destroy the reactor. For reference, this is an order of magnitude higher than nuclear reactors here on Earth need to achieve, which typically operate at about 300 degrees Celsius, as they are in effect just boiling high-pressure water. Ion thrusters do not come close to the operating temperatures that thermally driven engines do, and we can crank that voltage up high enough that the added mass of the ion barely matters. We are still achieving 10 times the specific impulse of traditional engines. Could we use a lighter propellant to increase specific impulse? Of course, but the advantages of using propellants like xenon and krypton are so good that the drop in exhaust velocity and specific impulse are worth it. Being inert, they can easily be stored over the long thrust cycles ion propulsion needs, making them the ideal propellant for long-duration interplanetary missions. Larger atoms like xenon also hold onto the electrons in their electron cloud much looser than smaller atoms like hydrogen, so it takes less energy to ionize xenon than it takes to ionize hydrogen. So this reduces the electrical power needed for the first step in our ion propulsion process. And most critically, higher mass exhaust improves thrust. This equation defines the thrust an ion propulsion engine can generate. Where ion mass forms the denominator of our specific impulse equation, it forms the numerator for our thrust equation, meaning an increase in ion mass will increase our thrust, which is the spec that ion propulsion struggles with most, a worthy trade-off. To use nuclear power to generate electricity in space and power our ion drive, we will need to figure out a way to cool the reactor core. For the nuclear thermal engine, the propellant acts as a coolant. For the nuclear electric engine, we will need a closed-loop coolant system, where we do not expend the coolant, but keep it in a cycle between the hot engine and a heat exchanger. The only method we have to dump heat overboard in space is through radiative cooling. So, a nuclear electric propelled spacecraft will need massive radiator fins where this coolant can pass through. This is feasible, but we have a long way to go with developing nuclear engines for space. And even with this added power, nuclear-powered ion propulsion would still be on the low end of thrust. In all likelihood, these ion-propelled engines will need to be a hybrid engine that can use chemical combustion for high-thrust maneuvers, or if the problem of long-term hydrogen storage can be addressed, a nuclear hybrid engine is extremely attractive, where our high-thrust burns can be produced by the nuclear thermal engine, and then through neutron-absorbing control mechanisms like these rotating drums, where one side is coated in a neutron reflector and the other is coated in a neutron absorber. By simply rotating these drums, the engine temperature could be lowered and switched to a closed-loop coolant system that could power our electric generator, and provide extremely high specific impulse and a gradual increase in velocity that could drastically cut our travel times to Mars, or perhaps allow humans to venture even further into our solar system and begin our gradual exploration and settlement of our cosmic neighborhood. This is an incredibly complex topic, with many nuanced and complicated ideas that I struggled to grasp until I found the right equations. I struggled to understand how thrust would require high mass flow rate, yet specific impulse is much higher when your exhaust molecular weight is low. The eureka moments all came from dimensional analysis of the equations and their derivations. Being able to understand the language of the universe is a vital tool in decrypting the world of physics. That's why Brilliant is such a great partner to these videos. Brilliant has curated 2 learning paths that will be perfect for both newcomers and experienced learners. The first, Science Foundations, will teach you everything you need to understand these videos, from chemical reactions to electricity and magnetism to classical mechanics. And then, when you are ready, you can level up by taking the Advanced and Applied Science learning path, which will take you through courses on special relativity, gravitational physics, and astronomy. Brilliant is the perfect place to hone your skills, with easy-to-follow, curated courses that will take you from knowing nothing to having a well-rounded understanding of the building blocks of an engineering career. Brilliant's thought-provoking courses will help you see STEM in a new light. They'll guide you from curiosity to mastery through storytelling, interactive challenges, and problems to solve. You'll start by having fun with their interactive puzzles and visuals, but with a little bit of persistence and effort, you'll be amazed at what you can accomplish. If you are naturally curious, want to build your problem-solving skills, want to develop confidence in your analytical abilities, or like me, find fulfillment in continual lifelong learning, then get Brilliant Premium to learn something new every day. If you are looking for something else to watch right now, why not watch my previous video about the insane engineering of the fastest aircraft in history, the X-15, or watch Real Science's latest video about the insane biology of the hammerhead shark.